the second derivative test, like the first derivative test, not a real test, but it's a test. So remember, we test for concavity, right? If the second derivative is greater than 0 for all x on an interval I, then the graph of f is concave up on I. That's part of the whole curve sketching, right? Max, mins, concavity, points of inflection. If f double prime of x is less than 0 for all x on an interval I, then the graph is concave down. Can we use the second derivative to find local maximum and minimum values? Question mark. The graphs of f prime, and f double prime are shown below. Okay, so here they're in color. And there, they're like dashed lines and dotted lines and solid lines. But they're all nicely labeled. So examine the graphs and complete the table below. So we're looking at an x-coordinate of -2, 1, and 3. We want to know what is it about f prime of x. So what were the x values? -2, 1, and 3. So we're looking here, and here, here, and we're looking for f prime of x, so it's 0, and 0, and 0. 0, 0, 0. Now, f double prime of x, is that greater than 0 or less than 0? So at -2, f double prime is greater than 0. At +1, f double prime is less than 0. And at +3, f double prime is, can't see it, but we can see it, greater than 0. Now, if f double prime of x is greater than 0, then is f of x concave up or concave down? Up. Okay, so CU. Less than 0 and greater than 0, up. Now, let's take a look at f of x. Does it have a local max or a local min at -2? So this obviously is a local min. So think about it. If you're concave up, then there has to be what? If you're concave up, then you've got to have a local minimum, right? If you're concave down, then you have to have a local, and if you're concave up, then you have a local min. So we can use the second derivative. If it's concave up, opens up, right, then it has a minimum value, so local min. If it's concave down, right, it's shedding water, that won't hold water, you have a local max. And if it's concave up, again, a local min. All right, so we could do that from the graphs, right? And it's just really looking at, well, okay, what do we look at? Critical values are where f prime of x is 0 or does not exist. In this case, it looks like a polynomial, so it exists at those values. What's the second derivative doing? Is it positive, which says it's concave up, or negative, and so on. So the second derivative test. If f of x is continuous function near x equals c, if the first derivative is 0, right, which is telling us what? It's a critical number, so it's saying you could have a local maximum there. And the second derivative is less than 0, which is telling you that it's concave what?
Down.
Down. So it's concave down, it has a local max. Okay. And then you can fill in the next one. Minimum. Of course he is. Okay, example 1. Use the second derivative test, which is in the box above, to show that f of x equals sine of 2x plus 2 cos x has a local maximum at x equals pi by 6. Okay, so what do we have to do? We're going to find the first derivative first, right? So, plan is, let's find the first derivative. Then what do we have to do with the first derivative? Evaluate it at pi over 6 to see that it's what? 0, right? Which then tells us that, okay, we could have a local max or min, and then we'll use the second derivative test by doing the second derivative, evaluating it at pi by 6 to determine whether it's positive or negative, and then we could say that the curve is therefore concave up or concave down, and therefore we have whatever, right? So that's the process. So first things first, first derivative first. Sine 2x, so that's going to be what? 2 cos 2x. Plus 2, no, minus 2 sine x. All right, then we should look at f prime of, so let's do f prime of pi over 6, which would be 2 cos, so 2 times 2 pi over 6, or pi over 3, minus 2 sine pi over 6. All right, so the cosine of pi over 3 is, I don't know, it's a half, right? So it's 2 times a half minus 2 times, and that's a half. Okay, so that's 0. All right, so it's all good, right? So we have f prime of pi over 6 is 0, telling us that there could be a local max or min. So now we'll look at f double prime. So I'll pause. You can calculate. Negative 2 sine x, and then another 2 minus 2 cos x. Too many 2's in there. Yeah, oh, sorry, that's a sine 2. It's sine 2x. Okay, so negative 4. So at this point, we could get fancy, right? You do cos 2x is whatever cos 2x is, one of the things, and you turn everything, or sine 2x. So sine 2x is what? 2 sine x cos x? But really, what do we need to do? We just need to evaluate this at pi over 6. Okay, so I think it's doable by just substituting in the pi over 6. If we were going to look at the second derivative and say, okay, where is that 0? So we were looking for intervals of, you know, concave up, concave down, but we're not, right? We're just trying to show that this has a local maximum. So keeping our eyes on the prize. So f double prime of pi over 6 is negative 4 the sine of pi over 3 minus 2 cos pi over 6. Which is, so what's sine pi over 3? It's like root 3 over 2, right? And cos, that's root 3 over 2. So we get negative 2 root 3. Negative 3 root 3. So what can we say about f double prime of pi over 6? It's less than 0. So f double prime of pi over 6 is less than 0, which leads to us saying that it is concave up. Less than 0.
Sorry.
And if it's concave down, then it has a local maximum. Which was what we were supposed to show, right?
That's also the question.
Okay, so we used the second derivative test, right? It told us something here, right? So we didn't have to, we could have done the first derivative, where was the first derivative? Here, we would have had to do stuff with the cos 2x and then factor it and then find the critical values, right? And then look around the critical values to say, well, so is it increasing or decreasing, and therefore do I have, but we didn't need to do that here, right? We could use the second derivative test, okay? So in this case, much easier, I think. Use a GDC. I believe that's a graphing or graphic display calculator. Graphing display, it's just your graphing calculator. To find all local max and mins for f of x is x minus 2 to the 4th plus 2. Do you even need a calculator to do that one?
Probably not.
Well, it's x minus 2 to the fourth, so what's x minus 2 to the fourth, right? It's just like a quadratic, but it's flatter on the bottom, right? Because it's a quartic. And it's shifted 2 units to the right, and then it's up 3. It looks something like this, I think. But hey, let's. All right, and there we are at 2, 3. Okay, so what have we got? There is a local. Thank you. Minimum. It's actually it's local and it's what? It's also absolute, right? But local minimum. At x equals 2, right? So we're often interested in that, and the local minimum is 2, 3, right? So the point 2, 3. Since there is a minimum at x equals, then f prime of is equal to, okay? According to the second derivative test, if f prime of x equals 0 and f double prime of x is greater than 0, right? Because we need it to be concave up, which implies a minimum, right? Greater than 0. Then there is a local minimum. Determine f double prime of 2 and explain the results. All right, so this should be relatively easy, right? I mean, just f prime. So what's f prime of x? We got a 4. X minus 2. And there's the inner function, right, whose derivative is 1. Okay, so we're not going to write that out. I think we've gone beyond that at this point. And the derivative of plus 3 is nothing there. Okay, so what's the second derivative? 12. X minus 2 squared. All right, so what's f double prime of 2? So 12, 2 minus 2 squared, which is 0. But we thought it should have been, greater than 0 because we have a minimum there, right? Darn you, second derivative test. Apparently you don't work both ways. So just because you have a minimum does not mean that the second derivative will necessarily match up with what you think, right? If it's a minimum, then second derivative should be 0. It's not. So in this case, the second derivative test is inconclusive. All right, so it's the second derivative test is not an if and only if, right? It's not a biconditional. It only works the one way, right? If the second derivative is greater than 0, then it's concave up and you have a local whatever minimum. And if the second derivative is less than 0, then it is concave down and you have a local maximum. If the second derivative is 0, or God forbid does not exist, then we don't know. We can't say anything about it, right? Then we have to go back to the first derivative and look what's happening around there, okay? So, which, might be what we're going to do anyways, right? We might just be doing first derivative anyways, right? But occasionally second derivative comes in handy. Come in handy on a multiple choice where you don't necessarily have to do all the work, right? Like if I've done the work for the first derivative, if I've done the intervals for the first derivative, if I've done the sign analysis for the first derivative, then I already know there's a local max or min, right? The second derivative can just verify that, or not verify it, well, sort of verify it, can let me know that, yeah, there is, right? Unless it's 0, and then it says nothing. Okay, so since second derivative is 0, is 0, comma, the second derivative test is inconclusive. I think that's got to be the word of the day, inconclusive.
You can't conclusively say that.
No, but we can conclude the lesson. Not yet. No, we still have like a pile of examples.
Yeah.
So the second, sorry, it's not over yet. So the second derivative test is inconclusive, right? It doesn't tell us anything. All right, I could write.
Waterboarding it.
Huh?
Try waterboarding it.
That's true. Still, I don't think it's going to talk. If it talked, then you're hallucinating. Find f prime of x if f of x is the square root of x squared minus 2x plus 1. Oh, okay, so go, do the derivative. Remember, you're the designated driver.
Just don't ride us off the bridge and keep making that joke.
Please, that's that joke about I want to die in my sleep like my grandfather, not like the passengers in his car yelling and screaming.
Exactly.
What do we got? We got a half. Then we got, because this is x minus 2x plus 1 half. So we got a half, and then we got this. We got all of this, and then we got this. So let's.
Yeah, you gotta put the quadratic negative one there.
That was always there. So 1 and a negative a half. Okay. So I'll write both of those just because, like if we, because this whole thing is about second derivative, so if we have to do the second derivative, you can do it from this as a product, right? You have a choice, or you can do it from this as a quotient. So your choice in doing the second derivative, right? Either one should give you the same answer. It didn't when I did it, but then I just messed up.
You can get the square root of the bottom. Yeah.
What?
That's x minus 1 squared.
X minus 1 squared.
Oh, x minus is?
Yeah, you can just equal 1.
Okay. Well, so if there's a local max or min, where is it going to be? At x equals 1. And when x is 1, what is this equal to?
Oh, it does not exist.
Does not exist, right? It's undefined, right? But that's okay. The critical numbers are when f prime of x is 0 or does not exist. So it could be located at x equals a critical number, right? It says if. Explain why the second derivative test cannot be used.
It doesn't exist.
Because this is just, well, it'll just end up being x minus 1 squared, right? Because you're going to square that. So it won't exist there, right? All right, so we say the second derivative is 0, inconclusive. In this case, the second derivative, so explain why the second derivative is local maximum at x equals 1 for this one, because the second derivative won't exist. Because the second derivative. So if the first derivative doesn't exist, then we know, if first derivative doesn't exist, it tells you there's a denominator which can be set to 0, right? And second derivative, well, you're just going to end up squaring that denominator, which could somehow be 0, so it could still be 0, right? It's not going to change its stripes. Because the second derivative does not exist. And I'm going all out, writing the words, right? At x equals 1. I always want to say when x equals 1. Any preference for that? At x equals 1? When x equals 1?
You use when x equals 1 and going to store the computer.
I
How could you?
don't know.
Insofar as x equals 1.
There we go. Perhaps we need something different, yeah. Determine all local max or mins. Oh, okay. Well, so if there is one, it's when x at x equals 1. It's when x is at equal to 1. So what do we have to do? We're going to have to use which test? The first derivative test. The second derivative test is what? Inconclusive. Right? Word of the day. What do we say? 1. Oh, not negative. 1. Sounded like me the other day. It's not a good thing. So what do we got for factors? We got x minus 1, and then we've got the square root of x minus 1 quantity squared. It doesn't matter. Square root's going to be always positive, right? And what else do we have? So that gives us, was it f? Gives us f prime of x. And that tells us that f of x. Okay, so x minus 1. So let's just take a number less than 1 and subtract 1 from it. I think that'll be negative. And if you take a number greater than 1, positive. That'll be negative. That'll be positive. So what's f of x doing in this interval? Yes, it is. And I just drew that. I was trying to, can I fix that? Nope. I could have put a down arrow on it, but then the line just wouldn't, because this is supposed to be evocative, right? It's supposed to tell us, oh, obviously at this point you have what? You have a local minimum, right? So first derivative test tells us there is a local minimum at, so there is a local minimum at x equals 1, and so what's f of 1? Yeah, it's 0, right? Yeah. We knew that, right? Because the thing is just x minus 1 squared. So local minimum 1, 0, right? 1, 0. You know what this graph looks like? Not really. I mean, think of it. So it's the square root of this. Let's go look at it. Wait, nothing happened. What does it look like? So square root, squirt. We'll just do the whole thing. What was it? X squared minus 2x plus 1? What is that? It's the absolute value of x minus 1. When you take the square root of something that's squared, you're really getting just the absolute value. I know, eh? The two examples above show that if f of x has a critical number at x equals a, where f double prime of a is equal to, or it, and being as there's enough space, I'll actually write that all out. Then the second derivative test is, word for the day, inconclusive. Now we need Mandy to take and say, I do not think that word means what you think it means. But I think it meant what he thought it meant, and I don't know, every time I watch that, but doesn't it mean that? No, what's the word? The word is inconceivable. What's the movie? The Princess Bride, of course, right? But doesn't inconceivable means what it? You've never seen. You have to watch it, seriously.
Let's go. Can we have a viewing party right now?
No.
Find. This is real life.
Find all local max and mins for x to the 4th minus 8x cubed. So it's a quartic which opens which way? Up, he says, after swallowing his coffee. All right, so what's the strategy? What are we going to do? Well, not really. I mean, we're finding local max and mins. We're doing the whole curve sketching thing, right? That's like tomorrow and the next 2 days. The whole curve sketching thing is, yeah, okay, so what's the domain, and what are the zeros, like, and what points can we find nicely, and then we'll do the whole, but we want local max and min, so we're going to cut to part of it. So what do we want? We want the derivative, right? Okay, that's easy. So what's g prime of x? Okay, now what are we going to do with g prime of x? We're going to factor that, right? Because we got to figure out. Now, it's a polynomial, therefore it does not exist, right? or it exists everywhere. So the critical numbers are
0 and 6.
0 and 6. Okay, so critical numbers. Zero and 6. Right, and what we're going to work at over the next few days is just sort of formalizing the whole curve sketching thing, right? And so, all right, so the critical numbers are 0 and 6. So that says, well, two things. Number one is the second derivative is really easy to find, right? So why not use the second derivative test? Okay, so what's g double prime of x? And look here, not here, right? We don't want the factored form for this. We want this. So it's just 12x squared minus 48x. Okay, and that we can factor. I mean, do we need to? Well, not really, right? I mean, because we're really interested in what's g double prime of 0. It's 0, so that's inconclusive. What's g double prime of 6? That's not 0, I don't think. All right, so let's work them both out and see what we get. So g double prime of 0 is equal to 0, so that's inconclusive. And g double prime of 6 is equal to, so I could factor that, but do I need, I don't know, 12. It's like, yeah, so who said no calculator? So that's 12 times 36, which will be what? 12 times 30 is 360 and 72, 432, I think. Minus, what? 6 times 50 is 300, minus 12 is 288. Equals positive. I mean, really, right? What matters? It doesn't matter what the second derivative is. That isn't actually a local max or min. What matters is the sign of the second derivative, right? Which clearly is positive.
You care about the
Yeah, you didn't. You could have written it out in factored form, really, and said, "Hey, this thing is obviously bigger than this thing," right? Okay, so it's positive. So what does that tell us? Tells us that it's concave up, which tells us that there is a local minimum. All right, so did it ask for the minimum or did it say find all? Yeah, okay, so it asked for the minimum. All right, so there is a local minimum at 6. All right, 6 to the 4th minus 8 times 6 cubed. Okay, so local min. So g of 6. Who knows your powers of 6? What's 6 to the 4th? 1296. Come on. 6, 36, 216, 1296.
Yeah.
You get a calculator.
Yeah. Gosh, guys. I totally didn't know.
8 times 6 cubed. That's going to be 8 times 216, right? So that's 1600 and then 80. So 1680 and then 48. So 1680 and 48. 1728. Now we can't just say that that's negative because we're actually finding a point. So we got to actually.
You can't just say it's negative.
Yeah, okay. 12, 6, that's a 2, 6, 12, 3, 4, 432. Okay, so local min.
It's negative.
Negative, right, because yeah, it was the subtraction was going the other way. Thank you. Negative 432. All right, and what's happening at 0 though, right? We don't know. So how are we going to figure out what's going on at 0?
First derivative.
We're going to use first derivative test. 0. I could sort of stop there, right? I mean, so at this point, you could, well, my critical numbers are 0 and 6. We could do the full.
No, I don't get it.
Oh, read the instructions.
I did, I've read it like 3 times.
All right, exactly. Fill that in. You could do the whole thing. So why ever do, so the question was, why ever do the double prime, right? Really what you're asking is, I think, why ever do the second derivative test?
Yes.
Right, because we do the double prime because we need to know concave up, concave down in the intervals, right? So if we're sketching the curve, yeah, okay, I know it's increasing because the first derivative, but is it concave up or concave down, right? Because you have four possibilities. It's concave up increasing, concave up decreasing, concave down increasing, concave down decreasing, right? I've actually seen nice little charts of that where it just sort of says, hey, f prime of x is greater than 0, less than 0, f double prime of x is greater than 0, less than 0. That's your four possibilities, right? If f prime of x is greater than 0, it's increasing if at the same time, right? So you make a little chart. It's actually kind of cool. Let's skip ahead to two pieces. We kind of do this, right? So you could say, it's like a Gantt chart. You ever do those Gantt charts? So f,
No, it's
I don't think it.
pronounced graphic form.
Graphic.
Exactly. Don't say
It's
square.
okay. So if the first derivative is greater than 0, then it is doing what? The curve is increasing, and if the second derivative is greater than 0, it's increasing and it is concave up. So it's going to look like this, right? I mean, not that part, because that's decreasing. So wait. Control. Okay, if the first derivative is greater than 0, it's increasing, but the second derivative, then it is increasing and concave down. Okay. First derivative is less than 0, then it is decreasing and concave up. Okay? And if the first derivative is less than 0, then it is decreasing and that's kind of neat, right?
Like one of those things that you learn.
Yeah, I saw that. I was looking up some stuff, and yeah, it's just sort of like, and so I just keep that in mind. We already know this, I think, but it's kind of handy to sort of have in mind. All right, so what were we doing here? So it's going to be Well, we got a 4, if you like. We got an x squared. We got an x minus 6, which is going to give us a g prime of x, and that will tell us the g of x. So, all right, this has already been done. It's like the cake is baked, and we'll just pull it over to that one. Well, you can just make sure that it. Okay, so what's happening here then at 0? Is there a local max or min? No. Right. So yeah, it's a POI. And this is a local min. Okay, now this we already knew, right? But the second derivative test was inconclusive, and the first derivative test tells us, hey, well, it's decreasing on both accounts, so it's got to be a point of inflection, right? And then we could go graph that. But it never opens, yeah. What was it? X to the 4th minus 8x cubed equals x to the 4th minus 8x cubed. Okay, and then we expect a minimum, right? So what should I zoom out? Out, but it's at negative 432, right? Out. Go out. Yeah, I could, but see, all that matters is this. Hey, look, it's at 6 and negative 432, right? Woohoo! We can do math without a calculator. Right. So it dips really low there, and whatever. Let's go back to standard there. Yeah. Kind of interesting, right? It just looks like a cubic there if you don't look at the whole thing. All right, so are we done? Final local? Yes, we have found all local max and mins. And absolutely min too, right? Go forward. Now, here, where would you use second derivative test, right? Because now we don't know what the second derivative is, right? I mean, it's some polynomial-ish looking, could be sinusoidal-ish. So the graphs of f prime of x and f double prime of x are shown, complete the statements below and explain how you determined the answers. So the graph has a, so what are the statements? We're looking for local max and mins. So what do we want to start off by finding? Wow.
Where's the f of x of f prime of x?
What did I moved something.
Yeah, no, you're right.
Okay. Whoa. Wait, control Y. Control Y. Control Z. Okay, stop now. What are we interested in? When,
F prime of x.
right, so there, and there. Right, so we want to know, okay, so when's f prime of x equal to 0? So here, let's, that's critical numbers, right? Okay, so what's x equal to? 0 and okay, so we got 0 and pi and 2 pi. Well, that implies that it's more sinusoidal-ish than polynomial-ish, right? Although the scale could just be in terms of. All right, so then what? So when x equals 0, what's f double prime of x? F double prime of 0 is 2, but we'll just call that positive, right? Well, okay, what do we want to say? We could say it equals 2. Equals 2, right? Which means that it's positive. Which means that that the graph is concave up. Which means that we have a local min. Okay, what are we going to say when x equals pi? So f double prime of pi is equal to 0. So what does that mean? Inconclusive. Okay, so let's come back to that in a minute. Or less. Or do you want to do it now? Let's just do it now. Okay, so then what do we have to go with? First derivative test. Okay, so as we approach pi, the first derivative is positive, and then it is negative. So first derivative is positive, says that we're increasing and then decreasing, which leads to a local max when x is equal to pi. Okay, so first derivative, so that's inconclusive. So first derivative test indicates local maximum at x equals pi. Okay, and what else did we have? When x equals 2 pi, then f double prime of 2 pi is equal to 2 again, which is positive. So that leads to a local min. Right, and the reasoning is exactly the same as here, right? I mean, that's just that. So the graph has a local maximum at x equals, we can't say what the maximum is, right? I mean, it could be anything, at x equals pi. And the graph has local minimum or minimum, so it has a local max or has local maximums, or that's how you have to read that. So this one has local minimums at x equals 0 and 2 pi. So that's it, right? I think that's it. I mean, an interesting thing to do here would be to try and sketch f of x. Right?
No.
Well, you know, it's just so. I mean, when you sketch f of x, its vertical position doesn't really matter, right? Like the derivatives, because what moves it vertically? Just adding a constant at the end, right? So we had x minus 2 to the 4th plus 3. Was that any different from x minus 2 to the 4th? Well, the minimum would be at a different point, but the derivative isn't any different. It doesn't matter if it's x minus 2 to the fourth plus 3 or x minus 2 to the fourth minus 762. The derivative is derivative, right? The curve has a shape, and therefore the slope at any given point on that curve is just dependent on the shape of the curve, not where the curve is located, right, as far as an up or a down. So if you draw f of x, I mean, we could all draw different f of x's in terms of its vertical position and in terms of how high we drew the maximums and how low we drew, but we'd have the same basic shape, right? Because what do we know? Well, we know that on certain intervals it's increasing, right? When is it increasing? When f prime of x is greater than 0, when it's positive, right? And it's decreasing when f prime of x is negative. And it's concave up when f double prime is greater than 0 when it's positive, and it's concave down when it's negative, right? So if you did want to draw this, I was kind of thinking of this because I thought, like, it sort of leads into the whole curve sketching thing, right? And it's like, can I combine everything into one thing? And I'm not sure I can. But what I would look at is, okay, where's the first derivative of 0? So here and here, right? Which means that between here and here, right? So the first derivative, first d, is positive. Okay, so the curve is increasing, right? And between here and here, right? So the first derivative, wow, first d is negative, right? Which tells you that the curve itself, the line you're going to draw, is decreasing. And at 0, you're going to have you have a max or a min, right? So if we're increasing and then decreasing, then there's going to be, we already figured that out, right? But there's going to be a maximum here, right? So somewhere I'm just going to peak, locally peak, right about here, right? And then it's going to decrease. Okay. Now at the same time, what else is going on? Well, when the second derivative is 0, right? So draw lines through where the second derivative is 0. So here, the second derivative is positive. So second d is positive, which says that it's concave up. And in here, the second d is negative, which says that it's concave down. And here, the second derivative is also negative. Second d is negative, so it's concave down. And here, the second d is positive, so it's concave up.
What does the third derivative say?
It would be the rate of change of the second derivative.
Yes, so what information does that give us about the main graph?
Nothing, I don't think. Because what else? Once we know, so we know that there's a maximum. Well, okay, we know it's concave up. This is concave up over here, and this is negative. So it's decreasing here, right? So here the first derivative is negative. So first d is negative. So this is decreasing. So it's so we know we've got a minimum at this point, right? So we're going to come down, and then we're going to go up, and at some point where, well, there's going to be a change in concavity right at this point, right? So we're going to change from concave up to concave down. Okay. So I sketched out something I think might work, but yeah, so do this in blue. The whole thing's a bit of a mess, but I had something looking like this. Okay, so second derivative is positive over here, right? So it's concave up. And then we hit a minimum. And we change to concave down here, so we're doing this. And then I want to change from concave up to concave down, so there's a point of inflection there. And then this is concave down, and we're hitting a maximum here. Okay, and then it's still concave down, and we're getting a, all right, oh, it's here. So we're getting a minimum concave down, but we're going to change, right? There's a point of inflection here. So concave down to up, and I missed the max. again. Okay. Anyways, something along those lines. An exercise in